In this video, we're going to look at exponents. And you've probably seen this before, that when you have a number that is written like this little small number up right here is called an exponent. And the larger number below the exponent is called a base. And this notation just means that we're going to take our base and we're going to multiply it by itself however many times the exponent tells us to. So in this case it's a 2, so we're going to multiply it by itself 2 times. So the value of this is 9. This is read as 3 squared, or 3 to the second power. And the reason we call this 3 squared is because 3 times 3 forms 9, which is a square number. It can be represented by a square array. Let's look at another example. This time the base is going to be 3 and the exponent is going to be 4. We would read this as 3 to the 4th power. And 3 to the 4th power means that I'm going to take the base, which is a 3, and I'm going to multiply it by itself 4 times. 3 times 3 times 3 times 3. Now, to evaluate that, I'm going to need to multiply it one step at a time. 3 times 3 is 9. Then 9 times 3 is 27. And 27 times 3 equals 81. The most common mistake that people make is adding these numbers. It's very easy to do 3 plus 3 plus 3 plus 3 and get 12, which means what you really did is you really multiplied the base times the exponent, and the exponent is telling you to multiply the base times itself that many times. So when you are evaluating exponents, I recommend you do it just like what I did here and do each step of the problem one step at a time so you don't accidentally try to add. Let's look at another example. Let's say we have a base of 5 and an exponent of 3. One way we could say this is 5 to the 3rd power. Another way we could say this is 5 cubed, because we can make a cube that is 5 by 5 by 5. So this means 5, the base, times itself 3 times. 5 times 5 times 5. When we're evaluating this, one step at a time. 5 times 5 is 25, and 25 times 5 is 125. Let's now see if we swap the exponent and the base and see if we get the same value. Let's put the base as a 3 and the exponent as a 5. So we would read this as 3 to the 5th power. It means 3 times itself 5 times. 3 times 3 times 3 times 3 times 3. When we're evaluating this, one step at a time, 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 equals 243. So we've shown that the position of the base and exponent, whichever number is your base and which is your exponent, absolutely matters. Because if you swap those two, the exponent and the base, you will get a completely different answer. So remember that when you're working with exponents, you take the base and you multiply it by itself however many times the exponent tells you to. Let's look at one last example. Let's say we have 10 as a base and 7 as an exponent. We would read this as 10 to the 7th power, and it means 10 multiplied by itself 7 times. Now we could actually go through and we could do 10 times 10 is 100, and 100 times 10 is 1,000, and keep going like this, and this would be 10,000 and so on. I'm not going to finish this, because what we can do is we can just look at the tens place, and we can say 1 times 1 times 1 times 7 times. 1 times itself 7 times is 1. And anytime we multiply by 10, we are shifting our place value over to the left. So we just need to shift it 7 place values to the left, which means I need 7 zeros. So 10 to the 7th power is equal to 10 million. We can then, knowing that, we can quickly find out that 10 to the 4th power is just 1 with 4 zeros, 10,000. 10 to the 5th power is a 1 with 5 zeros, 100,000. And 10 to the 9th power is a 1 with 9 zeros, which is 1 billion.